The next solution I want to talk about is actually a solution implemented in C++. And I want to describe their solution to a bunch of problems, or some of the problems, and then discuss how they actually solved the problem. Now, what they did in C++ is they used what's called smart pointers. So in order to introduce smart pointers, I want to first talk about a deprecated smart pointer, which means it doesn't exist anymore. It was deprecated, and its abilities were split amongst 3 different types of smart pointers. But in order to understand the concept, I think it's very important that we actually understand the original smart pointer. And the way the smart pointer works was the following. We had, it was called auto PTR. So they developed a class called auto PTR, which obviously was a template class, but I don't want to get into that. Okay, it was a template class. It could hold any type of pointer, but let's not get into that. In the public interface, they implemented the constructor. So there was an auto PTR constructor, which got a pointer of some type, right? You gotta understand it was a template. It was a template class. So let's not get into the template part of it. But the idea is they got some pointer of some type. And what it did was important here is that internally, they had a pointer of type whatever. That was internally. Now, the idea was to create an object that pointed internally to the actual heap. Now, since we want to create objects of type auto PTR, so we would create, let's say, auto PTR and stick some kind of, let's say, integer, whatever it is. So let's just ignore that part. Let's ignore the T part. And what happened was that you would send, for example, a new integer. Auto PTR, I have to get a name. Let's call it B. And you would send it a new integer, just as an example. Okay. Now, what that would do is it would this part of the command right here would actually create the heap, right? And it would send the pointer as a parameter to the constructor of the auto PTR. Now, what the auto PTR would do is it would use the internal pointer to point at the heap. Now, you're saying, what do I gain? Well, we'll get to that in a minute. But they also had to overload the star operator and the ampersand operator, because if we want to use B as a regular pointer, just write star B, we don't want it to be the actual auto PTR. We want it to be the heap memory that we're pointing at. So they had to overload the star operator and the ampersand operator, and et cetera, just make the overload all the stuff we need. I don't care right now. That's not the point, though, right? And the idea is that in the code itself, it behaved almost normal. It looked like a normal pointer, but it wasn't normal at all. What they did, which here comes the heart of the trick, what they actually did is they implemented a destructor. And what the destructor actually did was delete B. Now, why is it so important? Why is it such a smart idea? It was so smart, they actually called it smart pointers. What's the idea? The idea here is, let's use the mechanism of destructors of objects to clear the memory. Now, suppose we are in scope, in some kind of scope. Let's say scope foo. So we are within scope foo, just whatever it is, right? And inside here, we created an auto PTR. Again, I don't care how. And when you leave the scope, let's think what happens. So since this auto PTR B is actually created on the runtime stack, so when it goes out of scope, it is destructed. So right here, right before we have RIPB, right? Rest in pieces B, the destructor is called. The destructor will go and release the memory. And in a sense, we are reclaiming lost leaked memory. That's what we're doing. We are reclaiming leaked memory. So the idea behind auto PTR was not to have memory leaks, which was a major problem in C and C++ programming, that people did not, allocate stuff and forgot to deallocate them. And that's always used to be a big problem. By using smart pointers and specifically auto PTR, which I repeat was deprecated already, but the idea was to use the destructor mechanism of objects to actually deallocate the heap memory that was allocated during the construct, whenever you allocated it. Now, whenever you leave scope, all these memories are actually deallocated, and we do not have memory leaks anymore. So right now we have a solution to memory leaks in C++. So it seems that AutoPTR, which was actually part of the standard template library of C++, right, the STL, standard template libraries of C++, they chose to solve the memory leak problem using these smart pointers. The question that should just right away ring bells in our ears is that how can it be that such a prominent language is actually solving memory leaks by creating dangling pointers? Now, why do I say by creating dangling pointers? So let's assume we have two smart pointers and they're actually pointing at the same heap memory, right? And suppose the first pointer goes out of scope. Now you never deleted it. It just goes out of scope for whatever reason, even if you do delete it, right? You actually wrote, let's say delete, if it was actually, if you allocated the auto PTR, or if you put it on the one-time stack, it went out of scope, and this part actually got deleted. Now, not actually this part. Take that back. This part got deleted, right? Now, based on the rules that we actually said before about destructors taking the stance, so this part gets deleted as well, because the destructor is actually doing it automatically. It's actually deallocating the actual heap memory. Right? This is our heap. It's actually deallocating the actual heap memory. And notice what happens to this auto PTR. This auto PTR is actually losing its memory in a worse manner than it would have happened. It would have, if I would have left scope and not taking care of the destructor, so the heap would have stayed, right? This would have stayed, this would have been gone, the actual memory would have been gone, and I wouldn't have a dangling pointer. I would have a possible memory leak. By using the destructors of classes to actually reclaim memory leakage, what they're actually doing is solving the memory leak problem by increasing the dangling pointer problem. And this is something that should not make sense to us, because we are supposedly constantly claiming that the dangling pointer problem is the worst of the two. So why would a language like C++ do the other way around? It just doesn't make sense. In order for this not to happen, and as I said, it doesn't make sense that the engineers would actually solve the memory leak by creating dangling pointers. See, in order for this not to happen, we can't have two pointers actually pointing at the same heap memory. And they created a new concept. It's a new concept called transfer of ownership. Meaning that if you wrote, for example, this was A and this was B, let me just change the picture a bit. If the way this picture would come about is if you wrote something like B equals A, right? That's the way it would happen. So in this case, we would have what's called a shallow copy, right? This is a shallow copy. This was a shallow copy. And we would supposedly have two pointers pointing at the same location. Now, this can happen in other ways as well. And I'll show you in a minute how it can happen in other ways as well. But the idea is that the operator equals, the assignment operator was also overloaded. And what you had is transfer of ownership. the picture you see here will never happen. What happens is that when B equals A, what that means is that B steals the heap memory of A and A becomes null. That's what happens in smart pointers. What B does is it steals A's heap. And therefore, if A goes out of scope, no one cares. If B goes out of scope, nobody cares. Why? Because we can't have a dangling pointer. When memory of some pointer is actually assigned to another pointer, it doesn't just copy the values within it and points to wherever it was pointing. Or it doesn't do deep copy, which is something we learned when we learned C++ and we use copy constructors or stuff like that, or assignment operators and things like that. It doesn't do that. What it does is it transfers the ownership of the heap memory. That's what it does. So there is no dangling pointers. And this can happen another way as well. Think of a function foo, right? Think of the function foo where you send an order PTR A. Now the function foo is defined, wherever it is defined, as foo, and it gets an order PTR, and again, ignore the template part of it, right? And B. Now think of what happens. A's memory is being transferred to B. So again, we get a picture that looks like this. That's the way the picture looks. Within the function, B is the only one holding this heap memory. When you exit the function, so B gets rust in pieces B, and this memory gets deallocated, and that's okay. Why is it okay? Because A, wherever in this line of code, right? A already transferred its ownership. It's not dangling. If you try to access A over here, let's say star A, you would get an exception. Again, the null pointer exception, because the internal pointer within A is actually set to null. So this will work perfectly fine. And we get this amazing concept called transfer of ownership. Why do I say amazing? It sounds very funny to you. But this was developed further, and it created a new type of function calling in C++ called move semantics, and I'll talk about that in a minute. But this idea of transferring ownership allows us to actually deal with the memory leakage problem without stumbling over the dangling pointer problem, because there never is a dangling pointer. You never have two pointing to the same place. So we had to overload the equals operator, and we had to overload, notice, the ampersand operator, the copy constructed, all that business had to be overloaded, and to get this thing working. Now, you would say, but this doesn't make sense, that if foo calls A, and we have here a call by value, why on earth would A lose its memory? So the truth is that there was a new type of paradigm of pattern, should we say, of how to call functions. The way you called functions was A equals foo A. And the function would return, that void, it would actually return an order PTR. And here, right before we go out of scope, we say return B. So think what would happen. In a sense, on the way into the function, A's heap memory, A's data memory gets transferred to B. On the way out of the function, the memory gets transferred back to A, or to whoever it equals to. So when you continue with your A, there's no exception, everything runs okay, everything's still okay, and we keep running, and we get the look and feel that we were expecting to get, that A does not lose its memory, and we keep going, even though it actually lost its memory and got it back. Okay, now as I said, this is true of functions. When it comes to assignment operators, this is not true. A actually loses its memory, and this is called transfer of ownership, which was something that was actually put into the STL library in order to solve our problem. So let's discuss this again. We have a problem with pointers. We have memory leaks. We have dangling pointers. We went and we created a memory leak solution by using the destructors of objects, right, to deallocate dynamic memory that was allocated within whenever the actual pointer goes out of scope. Now, that supposedly created a dangling pointer problem. And we can't have that because we're constantly claiming that dangling pointer is worse than memory leak. And therefore, we create a new concept called transfer of ownership. And we transfer the ownership from one to the next. And we pass like a race, like we pass the buck from one to the next. And the idea is that no two own the same heap at the same time. So if anybody goes and actually goes out of scope or gets deleted, and the destructor goes and deletes its memory, no dangling pointers are created. Now you might say, yeah, but A is dangling by definition. Well, that's not true. Because as I said at the beginning of today's lecture, if I know that I lost my memory by having a null pointer or exception or whatever it is, that's fine. Because I can go and do a graceful degradation and do something else. The problem is that I don't know. And in this current system that I'm describing, you do know. And since you know, then everything's okay. There's no memory leaks, there's no dangling pointers, and we're in business.